So we will continue our foray into this weighted maximum matching, and today we will look at the following paper, or rather a version of for this. Let's see what paper is this. Okay, so this is paper by a 2+epsilon approximation for max weight matching in the semi-streaming model. Okay. So we'll do this 2+ approximation for maximum weight matching in the semi-streaming model today. And this is a paper by Ami Paz and Gregory Schwart Schwarzman. Okay, and this appeared in Soda 2017. Okay, and this is state of art. Okay, this is state of art. So when I say state of art, you have to be careful what I mean by state of art. Okay, state of art, when I say just one pass. Okay, there has lots and lots of literature where people have tried to compute better and better algorithm, and but using more and more passes. Okay, and there is a recent algorithm which says that you can do in order root m passes, you can actually compute exactly. Okay, but we will not get into those. Okay, this is like beyond the courses, but this is something which I would like to talk about. Okay, so let me start. Last time I was trying to talk about this local search. So let me give you a very simple proposition, which will be a fulcrum for all our algorithm today. Like, it's a really simple algorithm. So even if you don't take anything non-trivial out of this, you should take this algorithm definitely out of this, and the methodology which is behind this tool. Okay. So this is something which I first encountered in 2001 when I was learning to do, or 2002 when I was trying to read feedback vertex set approximation, factor 2 approximation. It has come, and I don't think it ever sunk into my head why it worked, but it worked. But in retrospect now, it's like it's just a 2-line algorithm. Okay, so what is my proposition? Okay, proposition is very simple. Okay, so I have been given a graph G, V, E, and a W. Okay, so now this is a weighted graph. Now let W1 and W1 bar be two arbitrary weight function. Okay, it's a two arbitrary weight function. Okay, and possibly even negative. Okay, so this weight function could also take negative value. I'm not saying that these weight functions has to take positive value. So even though you might have started with W, which is all positive, but my W1 and W bar could be two different functions where the weight function could be different. Okay, arbitrary functions on the edges of G. Okay, such that W is equal to W1 plus W1 bar. Okay, and now here's a good property. Let M be a maximum matching, or I think maximum matching is a wrong word. Let M be an alpha approximate, okay, matching alpha approximate maximum weight matching of G with respect to W1 and W1 bar. Okay. So what is the good property of M is it's an alpha approximate maximum weight matching of G with respect to W1 and W1 bar simultaneously, right? Okay. Then our claim is then M is also an alpha approximate maximum weight matching of G with respect to W. Okay. So let's understand the statement of proposition. What I'm saying that given a weight function on my edges, I have a weight decomposition into W1 and W1 bar. And suppose M is an alpha approximation to maximum weight matching of G with respect to weight function W1 and W1 bar simultaneously. Then actually if I take M, then M is also an alpha approximate maximum weight matching of G with respect to the weight function W. Okay. So the proof is very simple, like two-line proof, but it gives us, and I have specialized my my proposition with respect to maximum weight matching, but you will see there's nothing about maximum weight matching. You could have taken any maximization function, maximization problem, and the same lemma could hold if you could come up with an idea that you come up with a solution which is simultaneously alpha approximation with respect to one weight function as well as with respect to the other weight function. Okay. So now suppose M star, M1 and M1 bar are optimal max weight matching. Okay. So M star is with respect to weight function W, M1 is with respect to weight function W1, and M1 is, so this is an optimal solution. Okay. Now, so what we know, weight of M star, I can write it down, is equal to weight 1 of M star plus weight 2, weight 1 bar of M star, right? Like, because this is where we have used the property that W is equal to W1 plus W1 bar. So what is weight of M star? It's basically sum of the weights of each edges. Now look at each edge, and you have divided those edges into weight function here and weight function here. So this is equal to this. Now, what do you know about W1 of M star? Can I say this, that this is less than equal to W1 of M1? Why? Because look, what is the property of M1? M1 is a maximum weight matching with respect to weight function W1. And M star, it's some matching, right? So its weight will be anyway less than the maximum weight matching. Similarly, I can say this is less than equal to W1 M bar. Now, why? Because these are optimal matching with respect to W1 and W1 bar. Okay. Now, what do I know about W1 M1? What property do I know about W1 M1? Right. So what I also been given, let M be an alpha approximate maximum weight matching of G. Well, then weight of M1 is, say, now this will imply this is alpha times, okay, weight 1 of M plus this is alpha times weight 1 bar of M1 M, right? This is a property of M, that this is simultaneously an alpha approximate matching with respect to M1, with respect to weight function W1, and alpha approximate matching with respect to weight function W1. Okay, so because of this we have written this. But now what is this? Look, this is equal to alpha times W of m. Again, I have used now the property that W was an additive weight function. Okay. So this is, we are done, right? This is an alpha approximation uh, for G, right? We are done, right? So now you might say that, okay, fine. I mean, so there are two questions to understand. So we need first is how do we go about decomposing this weight function? How do we decompose weight function? That's the first question. And secondly, how do we get a solution that is alpha approximation to both weight function? Okay. So generally, this is why this method is called local ratio. Okay. So generally, how do we decompose this weight function? So for example, what we will have is a small structure, or I would rather say, not say small, but some structure where locally we can guarantee that solution must do something. Okay. And now what will I do? Define a weight function. That's very easy. Then what I do, I look at this local structure, define a weight function that is somehow that will give us alpha times guarantee locally. Okay. And for all other objects and for all other edges, vertices, whatever, or structure, okay, you put zero weight. Okay. And then once I have defined W1 and it is going to be an additive weight function, then once I define W1, W1 bar is fixed. Right? So once I either define W1 or W1 bar, the other weight function is a complementary weight function. You take W, subtract that, and you have got your weight function. Okay. So this is how we are going to apply. Now, what is the local structure for a matching? So let's understand what is the local structure of matching. Let's fix an edge, E. And now I told you that weight of E is greater than 0. Okay? And look at edges. Okay, so let's call this object, say, n plus E. So what is n plus E? All the edges that are incident on E and all the edges that are incident on E and all the edges that are incident on E and including E. Okay. And so now, what is a guarantee? Can you tell me from here? So if I told you this structure, I don't know about all the weights edges, but all I told you that I have an edge E whose weight E is at least 0, like it's non-zero weight. What can you say about maximum weight matching? Is it possible that maximum weight matching will not pick any? Is it possible that suppose I have M star intersection n plus E equal to empty? Is it possible at all? Do you understand my question? Look, I just focus on one edge and all the edges which are incident on that. Okay. And now my question is it possible that a maximum weight matching will not pick any edge in n plus e? Is it possible?
Yes, it is possible.
Why?
No.
Because you take
Because E is in it also, no?
Yes. So if it is,
it's only, of course not. No, it's impossible. No.
Right, exactly. So now we have found our local structure, right? And what is the guarantee on this local structure? Well, I mean, okay, now I know that weight of E is greater than or equal to 0, right? So in some sense, and I also know that somehow you need to pick any maximum weight matching is going to pick something from here. Now I'm going to take help of this and define a weight function. Okay, so what is my weight function? And look, so notice one thing, that this is greater than or equal to 0, right? Is it, and any maximum weight matching can pick at most 2 edges from here, can at most pick 2 edges from here, right? Maybe someone from here and someone from here, right? At most 2 edges, okay? And this is what you like to exploit, okay? And what more do I know? What more can I say? Can these edges, like if I look at the intersection, is it possible? So let's ask ourselves the following question. Okay, now I look at m star intersection n plus e. Okay, let's call this set of edges z, which is, I know that cardinality of z is less than or equal to 2. Now my question is it possible that weight of z is less than or equal to weight of e? Say strictly less than. Is it possible?
No, for the same reason, you can always remove these edges and pick E.
Exactly. So if the weight of z was less than weight of e, then I could remove this and I could pick I could pick this. So that kind of tells us that, look, weight of z is greater than or equal to weight of e. Agreed? This is my lower bound, right? Any optimum solution must pick something from here whose weight locally is at least weight of e, right? So now, can I come up with a weight function which say, look, and I want to use weight of e, and I say, look, with respect to this weight function, any optimum solution cannot pick more than some constant times, say, weight of e, okay? And that constant for us will be 2, okay? Okay, so now I've given that this is what it is, okay? Let's define the weight function. So my weight function is, I don't like this color, okay? So I'm defining weight 1 of bar, okay? Which is defined on the local structure, and then automatically we will get everything. So what I do, I said, look, all of you must pay something. Like weight of E must be paid, like maximum must pick something from here whose value is weight of E at least. Okay, fine. So I said, okay, in this round, let everybody don't pay more. You might have to pay more, or maximum matching will pay more or will take more, but let's say make sure that you at least pick this much. So what I do that, I put weight 1 is equal to weight E if, say, weight 1 bar of F, if F belongs to n plus E, right? 0 otherwise. So what I have done now, if you notice, for every edge here, right? If I draw this picture again, what we have done here, if you notice, what we have done, that the weight function assigns same weight to everybody here. right? This is what it does. Okay. 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 So now I have, so now that I have defined you W1 bar, right? I also know what W1 is, right? Which is nothing but W minus W1 bar. Okay. Now I just want to recursively solve the solution. Okay. So this is why the recursive algorithm. Recursively obtain a factor 2 approximation to G with respect to W1. Okay. Okay. So you have recursively obtained a factor 2 approximation to G with respect to weight W1. Okay. So suppose this is a matching M. Okay. This is a matching, say, M1. Okay. Claim. Okay. And what is the property of M1? Weight of M1, or rather weight of, say, M, weight with respect to M star is the maximum weight matching with respect to weight 1. This is less than or equal to 2 times weight of M1. Okay, this is what we are guaranteeing. Right? So this is what we are guaranteed. Now I'm claiming that look at this M1. Okay, this is also a factor 2 approximation with respect to W1 bar. It's funky, right? Why does it allow us to do this? Well, look at this. This is the structure we had, right? Everybody has weight of E, weight of E, weight of E, right? This is what? Okay. Now, any maximum weight matching in G with respect to W1 bar, any maximum with respect to W1 bar has value at least weight of E and at most twice weight of E, because all other values are 0, right? So now I focus on M1 and I check, does M1 contain any of these edges? Right? So what I'm saying that look at M1 n plus E. Okay, is this non-empty? This is a question for us. Is this non-empty? And there are two answers, right? Yes, no. If it is non-empty, then are we done? If M1 intersection n plus E is non-empty, are we done? My claim is, in this case, okay, M1 is already a 2 approximation with respect to W1 bar. Why? Well, M1 intersection n plus 1 is non-empty. So you could have picked up at least one edge from this structure, right? So now if I look at that edge, right? So look at that edge. It could be anything. So maybe I just picked up this edge, right? What is the value of this? Is weight of E. So my M1 has value WE, right? And I know the best matching with respect to weight function W1 bar, okay, has value 2 times W1 of E. Fine. If you picked up 2 edges, great. I mean, you have value 2 times W1 of E, and that is what your this weight functions allowed you to do. Okay. Or you could have just picked up this. So in any case, if you just picked up one edge, the M1 has value weight of E, right? Because all other edges outside has weight 0 with respect to W1 bar. So they do not count at all, but this counts. But the bad case is M1 intersection N plus E is empty. But this is not that bad. Okay. So then what I do, I define M, I add M1 comma E. Now, what is the property of E? What is the value of E here? Weight of W of E. So in W1 bar, in W1 bar, so I know that W1 bar of E is weight of E. So what is the value of W1 of E? Is WE minus W1 bar of E, which is 0, right? So weight of M is also equal to weight of M1 this, right? So with respect to weight 1 of M is also equal to weight 1 of M1 union E, right? So what is the property of M? M is still a factor 2 approximation to W1, right? So I have found another approximation, which is another matching, which is also a factor 2 approximation with respect to W1. But now we have ensured that this is M is also a factor 2 approximation to W1. Okay. So if I can recursively solve this problem, okay, and I got my solution, then what is the property we are able to do this? Because of this nice, beautiful weight function, weight decomposition, is that you give me any solution with respect to W1, I can, same set is either a solution, or I can do some local changes to my solution such that it has the property that, that it remains a factor 2 approximation with respect to weight function W1, but at the same time, now it becomes a factor 2 approximation with respect to W1 bar. Okay. And then we know by our proposition that if that situation happens, then whatever you have got is a factor 2 approximation. So one situation which I did not tell you. So for example, like I'm doing with respect to W1 and all weights are less than equal to 0, then just M is empty. Okay. Notice that this is what is happening, right? Look, so you will not get any trivial algorithm, right? Because if your solution from behind is not intersecting the object which I wanted, okay, then I add it myself. So even when all the weights are 0, you know that an empty matching is a good solution. But the moment, so what is recursion doing to you? Okay, so think of this way, that I discovered some structure. Okay, then I said, okay, fine. From here, locally, you need to pay me something. Okay, and that payment I reduced from everybody. Okay, I said, go. Now try to find a matching with respect to slightly lower optimum. Okay, okay, fine. Then I decompose again. You will decompose again with respect to some other weight. But now notice you will find another structure like weight of E. You will do another weight decomposition. So this is a recursive algorithm. Now, why it is not going to loop forever? Because in every round, okay, some edge weight of E becomes less than equal to 0. Say with respect to weight of 1 of E, some guy has 0. So when you go to weight, and look, and object whose weight becomes negative, it never becomes positive. It is always, what do you call it? It is always going to be negative. Do you see that? Because look, what is happening? So you fixed up some set of edges here, okay? Some weight for everybody. What is weight 1 of E? You make it 0. And from everybody else here, you decrease weight, right? From here, and rest is 0, so their weight is like same. In the next step, you might have found if all these are negative, then anyway you are not going to do anything. But it is possible that there is some other guy which is adjacent, and now with respect to this, you have defined some weight function in W1 bar. But what is going to happen here, W2? Well, whatever the weight it is going to decrease this particular weight even further. So someone who becomes negative is never going to become positive. And in every step, we make sure that at least one edge becomes weight negative. Okay, so this is how you apply this algorithm recursively. So, and each time finding a structure, finding an edge whose weight is non-zero and doing everything, it's quite simple. Okay, any questions so far? Right, so it's a very simple factor 2 approximation using local search, local ratio. Right? And why local ratio? You saw, right? An optimum solution here can at most be 2 times weight of E, right? But locally, you must pick weight of E. So, and that's a gap is factor 2. So locally, if I'm able to maintain a ratio of factor 2, then this is fine. So if you notice, very simply, look at lots of problems where say vertex cover or triangle hitting set. What is a simple approximation algorithm? You find an edge, delete both. You find a triangle, you delete it, right? Now, that automatically gives you a very local way of doing this. Okay, I find an edge. I know that, but suppose every weight has vertex. Like now, so the way you find a triangle, delete it. Now I want to simulate the same kind of object but for the weighted problem. So what I do now? Okay, fine. I find a triangle that which has at least say, let's say a triangle where all the vertices, right? So for example, if I was trying to do triangle hitting set, so what will I do? I will find a triangle, okay? I will find a triangle, okay? Such that all the guys are like say weight of V1, weight of V2, weight of V3, right? All these are greater than 0. Why? Because if there is no obstruction with, if there is no positive obstruction, let's say obstruction is positive, if all the weights are not this, means even if for all obstruction you have some vertices whose, whose value is like less, then you just pick up all the 0 guys, okay? And then you have got a solution with weight 0. So you don't do anything. But now if all are positive, then what do you know about your optimum solution? The objective which you know about your optimum solution is any optimum solution must pay minimum of these weights. Okay, so if W is minimum of WV1, WV2, WV3, right? So what should I do? What should be my weight function now? Well, I will tell you what should be my weight function. So I will say I will define some W1 of V is like, this is equal to W if V is equal to V1, V2, V3, 0 otherwise. Okay, that's it. Now, if you recursively would have found a solution from with respect, so this is like, sorry, this is W1 bar. If I would have recursively found solution with respect to say weight function W1, right? Then what I know, well, either you do not pick anything from here, okay, or you pick something from here. If you pick something from here, then I'm happy because, well, everybody, like from the recursively, if you found a solution, which is a factor 3 approximation to the recursive weight function, like with respect to W1, then I'm very happy because now I know that everybody from like the solution here, the best solution is W. And in the worst case, you'd have picked up all the three, which is like 3W. So if you picked up any one of these guys, I'm very happy, right? If you'd have picked up any one of these guys, then I'm happy because, well, fine. The problem is when you pick no one, then what will I do? I will pick up all these three guys and pay 3 times W1. Now, why do I need to pick all these three guys? Because then only I can ensure that feasibility solution, right? So because I have to show that the value of those weight function. So let's say, so what I do, this is my weight function, and suppose you'd have got a factor 3 approximation, say S, for triangle hitting set with respect to weight W1. Now, we have to ask ourselves that S should also be a solution with, and suppose this is a factor 3 approximation. S should be also solution with respect to W1 bar. So look, W1 bar has put everywhere weight 0. Okay. So the best solution here with respect to W1 is like W, and best solution, this is my best solution, this is minimization problem, and worst solution is 3 times W. Okay. So if S intersection, okay, so let's say if S intersection V1, V2, V3 is equal to is not empty, then are we good? If S intersection V1, V2, V3 is not equal to 0, then are we good? Well, why we are good then? First of all, is S feasible solution? Right? S is feasible solution, there is absolutely no issue. The problem could be that okay, S picked something, S has to pick something from here. Why S has to pick something from here? Let's see.
Second, I'm confused. So it's triangle hitting set, so it should be feasible solution all the time.
It should be feasible solution all the time, right? Because I'm not doing anything to triangle. It's just that I have reduced the weight to something, right? So S is a feasible solution. Now, yeah, so we don't have to do anything. So this is a feasible, this is much more easier actually, right? So S is a feasible solution to this guy. Now, but so S must be intersecting all these guys, right? Right? So the worst case is that it's a factor 3 approximation, but S might be intersecting all these guys, like must have taken everybody. And you might have to take one guy. So S intersection V is not equal to phi as pointed by Piotr. But now, look, if S intersection V13 is just 1, then you paid W, that's great. You locally had to pay W. If you pick 2, you pay 2W, but maybe you had to pay W. But you pick 3, all the 3, you had to pick 3W, but you picked W. And that's it. Right? So this is a factor 3 up. So S is simultaneously a factor 3 approximation also for with respect to weight function W1 bar, and then you are good. Okay, sorry, my mistake. Okay, for minimization problem, it has to intersect. So it always be feasible. All we need to show that simultaneously it is a factor 3 approximation with respect to both function. So while with respect to one, it is inductively guaranteed, and with respect to other, because, and look, this is where we use the fact that here all these guys have the same weight function, right? like same weight, W. And that is why we can say something. But it is not necessary that you need to put all the W. All you need to ensure that you have some kind of locally threshold of what it is and what it is not. Okay. So this is how you can convert any factor 3 or any factor alpha approximation when you want to hit some small obstruction in what is that called? If you want to hit some small obstruction from unweighted to weighted. And this is why people don't talk much about like these things. Okay. Okay. So now going back to my matching experiment. Now I would like to write down this algorithm sequentially. Okay. What I mean by sequentially, not recursively, but sequentially. So let's, okay. So here's my algorithm for matching, which I told you with respect to this weight decomposition. So first, let W1 equal to W, I equal to 1. And I'm going to define the stack F initialized to be empty set. Secondly, iterate over the edges E one by one in an arbitrary order. Okay, so there is no, okay. So I ask first, if my current weight of this edge is less than equal to 0, I say go to the next edge. Okay, you don't do anything. Second, otherwise, now say EI is equal to E, and what will I do? Push EI to the stack. Okay, so I pushed EI to the stack. Okay, see, for each F in n plus EI, what will I do? I'm going to define this my weight function. Let Wi plus 1 is equal to weight of I minus weight of EI. Okay, D set I to I plus 1 and go to next edge. Okay, and third, unwind the stack, okay, and create the max match weight matching, okay, M greedily in the stack order. Okay, so let's just try to understand what this algorithm is trying to do. Okay, this is exactly the same algorithm. Okay, so initially my all weight function is like W1 is all W. Okay, now I find the first non-zero edge. What should I do? Do you remember what we did? We looked at this edge and all its neighbors, and we reduced, like and we've made a weight function which was nothing but equal to this weight in all its neighborhood. But I don't want to do this because I'm trying to imitate sequential recursive algorithm. So I said, okay, fine. At this point of time, let me define a new weight function, which is nothing but it keeps every other weight same, except for this and all these neighborhoods, it decreases the weight of all these guys by my weight. Okay, so this is what is happening here. Okay, you set equal to I plus 1 and you go to next edge. Okay, and at the end, I will unwind the stack. And so what will be the, at the end, what will be the edge which will go in? It's a last edge which has a positive weight, right? And that's it. So what happens is that for any I in the above algorithm, right, what is happening? So W plus I plus of F is equal to weight of I if F is in N plus EI and 0 otherwise. Okay. And what is your Wi? Is basically Wi plus 1 plus Wi plus 1 bar. Okay. So this is a sequential implementation of that recursive algorithm, right? So I find an edge, okay, and I reassign my weight functions. So this is like, what is my, so notice, like when I say this is a weight function, so think that in the beginning, I have say E1, E2, and EM, okay? And I have W1. These are my weights, okay? Now, what is this step does? I found an edge, and I say, look, take this edge and reduce. So what is the next weight function we'll consider? So you will find some edge whose W something is greater than 0, right? So then what you do, you look at, suppose these are those edges, and what will you do is that you leave all those other same, but for these guys, whatever their corresponding edge is, you subtract the weight. So this is your second, right? Then you again find something. So what will the W3? Again, you find, maybe you found some, now given this, so suppose this gave to this, okay. So now I found some another edge, say E prime, right, which was greater than 0. Then what I will do, well, now maybe those edges which are there, I don't, but maybe for some, I make more changes. Maybe now suddenly there is no more changes here. So suppose this is, I only show the changes where I'm going to make. Whatever was the previous, maybe now some new changes has happened. Okay. So what is the meaning of this? So now here you subtracted weight of E. So now at this stage, you will subtract from here weight of E. You already have subtracted. This is how WT was. Now you also subtract W weight of E prime. Now this weight of E prime is, what is the weight of E prime? Not in the beginning weight, because recursively you have called your algorithm on weight function W2. So this weight will be with respect to weight 2. So basically what we should be actually saying here is not W, but with respect to weight W2. Okay. So now the subtraction will be, the W2 we have got, say W1, which is same as W in the beginning. But here I have subtracted W to E prime. Okay. And similarly here, there was no change here. So this is going to be, W2 of whatever it is minus W2 of E prime. But this is same as W1 because this is the first time happened. So you see, this is how progressively weights are changing. And at the end, what happens is that you have some weight function, which is basically makes all these guys negative. Okay. Now, what I'm doing, so this is what this algorithm is. Now, so what have you added to your stack? You only add an edge to your stack. So let's ask ourselves, when do I add an edge to the stack? I add an edge to the stack when this is some E1 prime, E2 prime, EL prime, when these are non-negative edges. Okay. I do not add edges which weights is at most 0. Okay. And when I do a stack order, what I'm doing, I'm going to find a maximum weight matching. Okay. Maximum weight matching in the stack order, in the sense that which was the last guy edge I added to my matching. Okay. I add this. Then the next edge I pop from the stack, I check. Can I add this edge? I'm not talking about weights at this point of time. Can I add this edge? well, I may not be able to do it, but let's just add if it does not intersect any previously selected matching. Okay, any previously selected matching does not intersect selected matching edges. Okay, so this is how you greedily do it. Okay, and then you claim that this is a factor 2 approximation. Okay, so even if you do not understand that why this is a factor 2 approximation, since we will see, this is basically an implementation of that recursive algorithm in this. Okay, so even if you don't see a proof why it's a factor 2 approximation, it's okay. I mean, we will do a proof anyway, but with a slightly different objective. But suppose I wanted to implement this algorithm in streaming, what are the issues we are going to face? Do you understand the question? If we wanted to implement this simple recursive algorithm in streaming, how will we go about implementing it? Okay, so there are two issues to handle. First, I do not have this amazing access to all the weights at the same time. I do not have access to this weight vector, which I'm writing it, which I showed to you all the time. I just do not have this access. Okay, so I need to do something. Okay, right? I need to do something that allows us to somehow, in some sense. So what I mean by this is that what do you want to do it? So I don't know. So let's try to understand the difficulties. Okay, and so suppose now my edges are coming in streaming. Okay, what questions do? So whenever an edge comes, what two things you ask? You ask yourself, whatever the meaning of that is, with respect to current weight function, is, say, W tilde is my current weight function, is greater than 0? That's the first question you need to ask. Right? So if you had the whole current weight function, then there's absolutely nothing to worry because you can check, but you do not have current weight function. Okay. Secondly, what you want to do, if this is the case, now you want to create new weight function. And what is a new weight function? Well, for all f in say n plus ei, what I want to do, I basically, my new weight function is for all f in n plus ei. I want to make some changes. What is the change I want to make? Well, I want to suppose this is like, so suppose W tilde tilde is same as W tilde except same on all f not in n plus ei. And here, what is the change I want to make? The following change I want to make. W tilde f minus W tilde ei. So this is what I want to do. But at this stage, I don't even know n plus ei. Right? I don't even know n plus ei. Because maybe some of the edges which are incident to me will come later. So there's absolutely no hope of doing these things. First of all, I mean, so you understand the difficulty of doing this. And first of all, number of edges could be too much. So I cannot even keep all the weight function of the edges. Okay. But but that's one thing. And secondly, look, I need to do something with respect to weight function now for some edges which are only going to come in future. So there are lots of technical difficulties one can think of this, okay? But there are very cute solution to this problem which will come in a minute, okay? So this is difficulty number 1, okay? Okay. So now let's talk about difficulty 2. In stack, right? Stack could be difficulty. In what sense? You might encounter omega n square edges with some weight of this is greater than 0. And what does algorithm did? If your weight was, with respect to my current weight function, it is strictly greater than 0, please put me in the stack because I could be a possibility of being considered for this. Okay. So the way I look at this stack is the following. Look at the H, the subgraph, and this is a question which is which I personally find very interesting. And okay, so this is a subgraph H. Okay, and what is the property of look? But we also did not add some edges inside the stack, right? The edge weights whose weights were less than 0 equal to 0, you never added. So this is H. So let's say H is a subgraph of G, okay? And I want to call this, as you say, code set or whatever you want to call it. I'm going to define the notion of maximum matching code set or whatever you want to call it, okay? What is a maximum matching code set? Okay, it's first, it's a subgraph of G. Secondly, and let's say alpha maximum matching code set, and alpha approximation to M on H is an alpha approximation to M in G. Do you get my point? Do you understand the property of H? What is this? What is the property of H? H is a subgraph of G, and if I find a maximum weight matching of H, or if I find a good approximation to alpha approximation to M on H, then I can also scale this. Oh, this is also an alpha approximation to this is also an alpha approximation in G, right? So in that sense, my stack is storing a sparsifier, right? Or storing a code set, however you want to call it, okay? So that is the property. Yes?
But what about the size of H? Because like trivial example, H is equal to G is core set, right?
It's a core set.
Huh?
Yeah, you're right.
So do you impose any constraints? How small it should be?
Yeah, we will, right? And there's a trivial core set, which is very interesting, right? You take H as maximum weight matching.
Sure.
Right? So you do have a core set of size n by 2, right? And you have a trivial core set. So there are these, but we are trying to solve this problem. So what does it mean that this is, so something which is streamable or something which we can compute in the streaming setting. And we would show now, we'll show some point of time that we will be able to get some n log square n kind of sparsifier. Okay, and this is what we would like to compute. Okay, so but we are still far away from getting there. Okay, so first let's try to understand how do we handle these two. And so these are the two, like if you read their paper, this is what they are trying to do, but this is like I mean, it's not something which is very clear from their paper, but this is what is happening. Okay, so let me try to tell how do we handle the first situation. Okay, So what I would like to do is that I want to compute these weight functions on fly. Okay, look, I'm not interested in, look, like notice that whenever you have some weight functions, okay, something is happening. Okay, can I store some information that will tell me what is my current weight is? Okay, so let's just try to go myself an edge. Okay, let's just zoom into an edge. Okay, here it is. Okay, okay, so this is a sequence of edges which will come. Okay, blue edges comes first. Red edge, and then green edge. Okay, in whichever order, doesn't matter. Okay, so what should be the weight of this edge when all the blue edges has come? Suppose first comes, I wrote on purpose, maybe this is not 32, maybe too small, let's say 100. Okay, so suppose first one came. What will the operation be if the first one comes? What will the operation one will do? Right? Let's see how the edges of weights of 100 will be modified. So when one edge will come, what will it do? It says, okay, I am going to decrease the weight of all my neighbors by me, 1. Okay, so this guy will turn to 99. Next 4 comes. He says, okay, but notice if 1 has come, what is the weight function of 4 after that? Look,
3.
Exactly, right? So I cannot look into these things just like that. So let's focus on, let me write down, like if we want to understand this properly. So let's just focus on these weights. Okay. So in the beginning, so like suppose I have 1, 4, 5, 100, 8, 6, and 7. So this is the order in which, like, okay, let's not say order. That's just wrong word. Okay. So first say 1 has come. So clearly after this, the weight function is going to be 0, 3, 4, 99, 7, 5, 6. And suppose next this edge came, 4 edge. But now it is going to decrease all the edges by its own weight, right? This is what is happening at that point of time, right? So what will this become?
Sorry, why 8, 6, 7 got decreased weights?
They should not decrease, right? Because
In some cases, they could be
Oh,
decreased.
no, they shouldn't. That's just wrong.
Yeah.
They should, yeah, because that is not even incident to this edge.
yeah, correct.
Sorry, my mistake. Okay. Now suppose 4 came. Okay. So 4 is, but now the 4 value is 3 here. Okay. So what will it do? It will change all its neighbors by its weight. It decreases its weight. So this guy will become now -3. Okay. And what will this become? 0. What will 5 become? It was 4, so it becomes 1. And this guy will change by 3, so it becomes 96. And as you rightly pointed out, these people have absolutely no change. Now suppose 5 came. Okay. If 5 comes, now it is going to decrease this by 1, this by 1, 0, it will going to decrease this by 95 and 8, 6, 7. Okay. Now suppose 8 came first. Okay. So then the weight function becomes -4, -1, 0. Suppose 8 came first. So now what is going to happen? It is going to make himself 0. And now what is happening to these two weights? -2, -1, and this will become 87. Is this okay?
Yeah.
Piotr, is it fine?
Yeah, yes, fine.
Okay. But now if the edge 6 will come or 7 will come, they have no role to play. Right? Because their weight is E is less than or equal to 0, then what is my algorithm did? It just moved on to the next edge. It didn't do any to the weight. It only does if it encounters an edge with a positive weight. Okay? Fine. So, I mean, but I want to focus on myself, focus on 100. Okay? So, what does 100 signifies? 100 signifies changes done by all the edges which were incident to say this U and V that came before me. Okay. So if somehow changes are stored at a vertex. Okay. So I have a potential phi V, okay, for every vertex. Okay. So suppose I had a good potential function. Okay. So what potential I would like to do is the following. Okay. So what I would like to store here, okay, it is some kind of for each V. This is something which you're going to store. So suppose I would have stored at this, okay, let's see what is the change at U, okay? And then the definition will automatically come. Let's keep the changes, okay? So rather than storing at the edges, I'm going to store the changes which has been done to U. So in the beginning, I am 0, okay? So now the first guy came and how much changes did he make to himself? So I'm going to unwind in opposite. So 1 came, it says, okay, I need to remember for E, which is going to come in future, that look, there was an edge who came and wanted to delete 1, decrease 1 for E. But since you were not there, he didn't do it. Okay, so I'm going to store that information for him. Okay, so 1. Next, so now suppose I have this information. Notice the moment the second edge comes, he doesn't need to know the current weight function to know his weight function. Oh, someone has come before me, and whatever my weight is, he wants me to decrease by whatever U had stored and then consider my weight function. Okay, fine. Am I still positive? If I am, then good. If I'm not, then so then I know what is my current weight function is, like what is my current value is. So at this point of time, the current value is like when the 4 came, oh, my current value is I must delete 1 from, look, and I need to do this not only with respect to U as well as my other endpoints, but I'm just ignoring that for a moment. So at this point of time, he said, look, I'm positive, my value is 3, okay? I'm going to make, I'm going to go inside the stack at this point of time because I'm positive. But look, for future edges, whenever you come, you must know that there is a contribution of 3 from this guy. So any edge which in the future will come must subtract its weight by at least phi U and some phi V, whichever happens. Okay. So basically, I'm going to store change edge. right? So whenever I come much later, many edges would have come and they would have decreased this. So I'm storing how much decrease they would have done, like all the edges which are incident on you, all the edges which are incident on me, how much changes they would have done. So now phi u changes to 3. Look, and then 5 comes. He says, oh, already some guy has come and they have decreased, like they wanted to decrease 4 from me. So, oh, but still I'm positive, I have 1. So fine, I go inside the stack and I add 1 to u, right? Now look at 5e. Okay, 5e first came 8. Okay, and now suppose v was 0, 5v was made to 8. Rest of these two guys, when they come, they check, oh, someone already too big has come and decreases. I'm not going to the stack, done. So now when E comes, what he needs to do? He needs to say, okay, what is my weight? I know my current weight because I see mine. Oh, I have to remove whatever edges which has come and wanted to decrease phi u, whatever has come and wanted to decrease from V, right? So my actual weight is weight of E minus 5. So this is like 100, right? 3, 4, 5 minus 8, which is 87, right? So basically at every vertex U, I'm going to store what is my current change, like what is the changes which has happened. Okay, is the idea clear? Okay, so I'm going to have, oh, it's 342. Okay, 5e, it's a potential. So let's at least, let me see if I can do. Potential is the total sum of the weight, okay, already reduced from the edges, incident to the vertex V, due to edges that were incident to V and put in a stack before. Okay, so notice what has happened. This now I'm not keeping track of any weight functions or something. All I'm keeping track of n potential. Okay, and as I told you, right, the maximum weight is like W is like poly in n. Okay, so let's do another weighted matching algorithm with new potential function. I'm still not handled that stack can be too much. Okay. Define a stack S, which is empty. And also for each vertex V, I have phi V, which has been initialized to 0. Okay. Now, second, for any edge E equal to U comma V in E, if weight of E is less than equal to, what is this? Phi of less than equal to phi of V, okay? Then move to the next edge. right? Because what is this? If phi u signified and phi b signified, how much should I be decreased? Then I know my weight is negative. I shouldn't be worried about myself. Else, now push e to the stack. Okay, and what else should I do? Let's define weight prime of e is weight of e minus phi of u plus phi of v. So this is my current weight, or this is my change. Okay. Now this should be registered, right? So whatever will I do? I say, okay, fine. Whatever may be the value of phi u was, now please register the changes which e needs to do, and you do it to both your endpoints. Okay. And third, unwind the stack and create the matching in the stack order. M greedily in stack order. That's it. That's an end of the algorithm. Right? So now, rather than doing this, now I have a potential function. Okay? What it does, so basically it says, look, what is my current weight? If it is negative or less than equal to 0, then move on to the next stage. If I somehow have been able to encounter that, yes, I am a positive weight is, then let me go inside the stack and let me notify u and v that, look, any edge in the future will come. This is my contribution to the change. Okay, and that's end of it. Okay, so this is an end of the algorithm. Okay, but so if you understand what we did for the first trivial weight, this is exactly the same, but now it is with respect to the potential, and it requires proof. I do not want to say that, okay, it just follows from there or something. Okay, so I still have 10-15 minutes, so let's attempt a proof. Okay, it's not very hard. Okay, because it is ultimately all we are doing is unwinding the algorithm which we did before. Okay, so let M star be the max weight matching. Okay, now, and let M be the matching returned by our algorithm. Okay, and so I'm going to assume that my edges are coming in this order, E1 to En. Okay, so what is my Mi? Is M intersection EI to En. Okay, and now I'm going to define a new edge value. Okay, so I'm going to define, okay, weight of E. Okay, so think of this as a long big vector I'm going to define now. Okay, after each round is going to be equal to weight of E minus phi u of u minus phi u of v, where are the potential values just before the ith edge in the stream has arrived. Okay, so if nothing has arrived, potentials were 0, so this is what you get, W1, right, which is equal to W. So this is your weight function. Okay, when an edge comes, okay, when an edge comes, suppose that edge you didn't bother. Like now edge is not added to a stack, right? Then we don't make any changes to weight function. Then suppose you are at wi, okay, wi plus 1 you just copy, right? So these are not the changes. This is just for the analysis. Algorithm is doing whatever it was doing. It is done. But now, if a new edge comes, okay, so suppose this is wi and wi plus 1, okay. So if ei does not go to a stack, okay, then doesn't go to a stack, then wi plus 1 is wi. And suppose ei did go to a stack, then what happens? Okay. So how did we define w? So we would like to understand how wi plus 1 and wi are related. Okay. This is what we have to understand. And I think we'll end there today. I don't think I can complete the proof. Okay. Okay. So let's just try to understand what happens to wi plus 1. So by definition, what is wi plus 1 of an edge? Wi plus of an edge is nothing but, if you notice, that, well, it is weight of E minus phi I plus of, say, E equal to uv, right? U minus phi I plus 1 of v. Now, suppose EI and E have nothing in, like, have no vertex in common, right? Then what happens? Phi I plus 1 of U is phi I plus 1 is phi I of U, and phi I plus 1 of V is phi I of V, right? So in this case, wi plus 1 of E is weight of E minus phi I of U, sorry, right? Minus phi I of V, which is same as weight of E. Makes sense, right? You didn't do anything to the weights, potentials. But now, the more interesting cases. This is your EI. And this is where you have made changes, right? And suppose here is my U and here's my V. V is somewhere here. Now, suppose this is my E. Now let's try to understand what is a weight I plus 1 of E is by definition weight of I minus potential phi I plus 1 of U plus potential V. Well, with respect to V, potential did not change, so that's perfectly fine. But what is this? Right? So if you recall correctly, let's go back to our algorithm. Phi of U in that stage will be whatever the previous phi is plus the changes, weight prime of E. Okay? So let's just go back and write it down. Okay? So this is nothing but, this is phi of U plus changes with respect to EI. This is what it is. And this is phi of V. Okay? Okay. Okay. So this is, let's see, what is this? Okay. Let's try to understand this. Okay. Let's just try to understand this. Some simple thing here. This is not something very hard, but what I would like to show here. Okay. So let's try to see. Okay. So this is, sorry, this is phi I of u. Okay. So what is this? It is weight of E, right? This is weight of E minus phi I of u minus phi I of v, right? This. But what is this? Is this correct? Is it the weight of E with respect to I, because weight of E minus phi of u and with respect to I. Okay. So the only thing which is remaining here is this extra term of weight prime of EI. Okay. But what is weight prime of EI, if I recall correctly? I don't know why it has become like this. Right? But what is this quantity? So what is the weight prime of EI? Is weight of E minus phi of U, right? Minus phi of V, which is nothing but weight of I of E, right? So this I can write it down as nothing but this is weight of I with respect to E. Okay. So what we are able to show now is that weight of I plus 1 of E is nothing but is weight of I of E. And weight of I plus 1 of EI is going to be weight of I comma E minus 2 times weight of I comma E, because you also have the changes with respect to V. So this is what we will be able to show, that weight of I plus 1 is, it doesn't changes with respect to this, any edge which are incident, but with respect to other, and this is what we actually thought, right? This is, so by current weight, and I drop by whatever the E tells me. So this is exactly, so I have a weight I, some guy. Now I'm going to the next weight function. What happens? To all the edges which are incident to me, I'm going to decrease their edge by my weight, which is precisely what Wi minus Wi is. Okay. And to me, generally I was decreasing it to 0, but now I don't care. I make it to negative. So this is what is happening with respect to the weight function. So this is exactly mimicking the weight function which we had created before, but this weight function we never create explicitly, but this is the property of the objects which we are going to keep, and this is good enough for us to guarantee everything. So I think it's 3:58, and some people have class at 4 o'clock, so I will leave now. So we will continue our discussion on this. We are very close to proving whatever we wanted in the next class. Okay, on Wednesday. Any question?
Saket, I have a quick question. So can you just go back to the last algorithm?
Or this one? This one?
Yes, this one. So
Okay.
here in the second step and A,
yes,
in the part A, you are saying that so if the weight is at most this much, so it could be, the weight could be, or
weight has to be negative, right? Because what is my current weight? Think of this way. So what did we do? What did we say? Look, what is my potential? My potential is amount and edge incident to U will be decreasing, and V is the amount of weight which the edges which are incident to V will be decreasing from me, right? This is what I'm keeping track at U and V. Right? So what is my current weight? My current weight is phi U and phi V. And if I have become negative, I should not be bothered, right? So
yes, but it cannot be 0.
It could be equal to 0, but then I don't care about those edges. I only put you in the stack if your weight is at least 0.
Yeah. So basically, like in the sequential setting, like if we had a local structure,
Yes.
then it could be the case that from the local structure you don't select anything, and then
Exactly,
we had
because the local structure is here. So what is the local structure? So local structure here is like, think of this way. So here this is says less than equal to 0, right?
Yeah.
Right? I have no guarantee or anything here.
Yeah.
Right? So I said, but in some sense, this is great for me in also in some world. You know why? Because look, I could pick up if my solution did not intersect this part, I could pick up anybody here. Or I could pick up just empty solution and I'm good.
Yes. So if you just throw away that edge, then
I'm not losing anything, right?
I mean, like in your solution, you don't have to select that edge. Like you don't have to report that edge if you just throw that away.
No, because it's a weighted matching, right? Imagine that every weight was negative, right? What is the maximum weight matching then? Empty set is also a maximum weight matching. You get my point?
So you don't have to report the matching at the end?
I mean, we will be able to get a matching from here. Because I'm creating this stack, right?
But last step in the algorithm actually gets a matching, right?
Yes. Look, so let's think of this way, as Venkatesh points out. No, but why did you become negative? Suppose I started with all positive, but why did you become negative?
Yeah, that negative is fine, but my
no. So let's just ask ourselves, right? Think of this way. So imagine that. Okay, so suppose whenever you are this, I drop you. Okay, this is my graph, right?
Right.
Okay. Now, if this is my subgraph at the edge, at the end, can you not pick any of the edges from here? Will you not pick any edges from here? Is it possible at all? So look, why did I become negative? Right? The reason why I became negative is because there was some edges which was selected in my edge, right?
Right.
Right? They forced me to become negative because they were too much positive.
Right. Mm-hmm.
So this similarly here, right? So your matching will be picking edges from here, so you will never be able to pick this anyway. That will be a property of your algorithm, right?
But is there a guarantee that one of those neighboring edges will always be chosen?
Well, if I show that it's a factor 2 approximation, yes. Or even if it didn't, I didn't bother. At least at the end, I have a matching, which I'm guaranteed that with respect to the original weight function, it is a maximum weight. Look, this is exactly the recursive algorithm, right? Will recursive algorithm touch this edge?
So if we go to the recursive algorithm, I think you had a step.
No, I never had any step.
Yeah, if you can you scroll down a bit?
This is my recursive, or this is my iterative algorithm.
Yes, if you scroll down a bit.
Yes.
A little bit more.
Okay.
Yeah, right here. So here you mentioned that. So before the claim that you are also going to extend the matching, right? So
no.
if
That was when I found a structure. Let's see. Then that's even more further. Okay. What did I show to you? Look, I assumed that weight of E is greater than 0. Then only I was decomposing my weight function. If all the weights are negative, okay, at some point of time, look at this recursive algorithm. It is not deleting any edges or anything, right?
Right.
Right? It does not. It's just decreasing the weight function. So now you reach a stage, okay? You reach a stage where all weights are negative. Do you need to do any more weight decomposition? You have not, like, at least this process cannot find any weight decomposition.
Right. Yeah.
Right. So at that point of time, what should I output as an output? I can output an empty set. That's the best.
Exactly.
Okay. So I'm happy.
Yes.
Okay. So you go back one step in the recursion, right? At that point of time, some edge was positive.
Right.
Right. And that is how you did your weight decomposition. Am I right? Just one step before, right? Now, what did I prove here? If you look at the proof, I said, suppose this is an edge with respect to you did your weight decomposition, and then everything became 0. Okay, this is the last step. So when you go back, will this case apply? M1 intersection n plus 1 is non-empty. Will this case ever apply? You understand my point? Suppose this is an edge with respect to which I did my decomposition. So this is why I got W1 bar. Okay?
Right.
And then I went to a W1 where all weights were less than equal to 0. Okay?
Right.
In that sense, you gave me M, which was empty. Right? Okay. But what did I say to you? That look, if M is an empty set, okay? M is an empty, then its intersection with n plus E is also empty.
Yes.
In that case, this M is not it is not a guarantee of max weight matching, right? Because one has weight 0 and other has a positive weight.
Right.
Right? So then what would have done in this case? Right? So I'm in the no case, right? So to empty set, I added the edge on which I did my weight decomposition.
Right.
And now I'm claiming to you that look at M, which is M1 union E. Let's go back all 0 weights. Okay. So for all 0 weights, any matching is a factor 2 approximation because the best solution is 0.
Right.
Right. In fact, in the next step, this edge has weight 0 actually. This is the important point. Okay. Not all. So this edge has weight 0 actually. Or I cannot take all, right? Hence, it's a factor 2 approximation.
Right.
Okay. But now I have added this edge, right? Because that is why with respect to W1 bar, I'm going to get a factor 2 approximation, right?
Right. Yes. So that was exactly my question. But we have already thrown away that edge. No.
No, we didn't throw away this edge.
In the
Its weight is non-zero. I put it in the stack. All the edges on which you would be doing probably weight decomposition. Okay, those edges I have put.
Okay, so you actually don't care about the edges which have already become non-zero.
So basically, what is happening? If you notice, there is a solution. There is a solution which consists of all positive, like all the edges which I have put it in the stack, right? Or all the edges on which I did my weight decomposition. I can actually find a solution from there.
Okay.
Right? And why? Because look at the last step. All edges are 0, right? In the next step, what happened? You picked up an edge on which you did your weight decomposition, you added it. That is how the algorithm will work, right? And that's a correct for this weight step. You go forward, right? You go behind. Either this is a remains a solution, then that's perfectly fine. Otherwise, you will add to this solution. Am I right? What will you add? An edge on which you did your weight decomposition. It was a positive weight, right?
Yes.
So I have that available to me, right? In my stack. I go further. Okay, either in the step before, that remains a solution, or it doesn't remain a solution because its intersection is empty. Then, oh, fine, if this intersection is empty, but then I have a weight on which I did my weight decomposition, right? Which is positive. I will add that, right? And did I discard all these edges in my stack? No, I have added all those edges to the stack.
Right.
So that is why you can easily forget. You can forget this. That is why when you do sequentially, okay, the edges on which you becomes weight 0, you can forget it.
Okay.
So it is basically unwinding this algorithm. Right? So you start with an empty edge, empty solution. You add an edge on which you did your weight decomposition. You go behind your recursion. Oh, now this is no more a feasible solution, or it's not a solution, simultaneous solution. Okay, let me add on which I did my weight decomposition. Oh, now it is simultaneous solution. Let me go behind. Another edge, simultaneous solution, go behind. So this is what is happening.
Yeah. Okay. Thanks for the clarification.
Okay.
Yeah.
Okay.
Okay,
So now, yes.
One quick comment. The last thing about potential and looking for whether the weight is less than 5u plus 5v kind of thing remind me of this primal dual algorithm.
It is primal dual algorithm. I mean, we could also write it as a primal dual, actually.
Yes, right? Okay, fine.
Yeah. So okay. Now that you mentioned it, let me say this. So let's write it down. Primal dual for the primal dual. Okay. These phi's are nothing but a feasible solution to vertex covered instance.
For the dual.
Yes.
Okay.
So if you're interested, I can also do analysis from there next time. I mean, I did today morning, but I was not sure that if all of people will be able to appreciate primal dual. So I thought that I will do with charging arguments. Like with just induction, basically. Okay, but you are right. These phi's are nothing. This is how you actually have defined these things. Like, I mean, at least this is what is a line written in the paper, right? That they were motivated by this, but they didn't know how to do this in primal dual, but this is their motivation of defining potential. Okay.
Yep. Thanks.
Yeah. Okay. Yeah, we are very close to, at least if I have not made mistake in my analysis of this algorithm, we should be very close to we need another 20 to 30 minutes next time to finish this algorithm. Of course, if I made a mistake in trying to simplify their analysis, then all are wrong, but okay, but I don't think so. Okay. So let's meet on Wednesday until, otherwise, unless you have other questions. Okay, so before you people go, I mean, how many of would you be interested in, say, since we are on graph algorithms, how many of you would be interested in doing some graph classes or parameterized algorithms of in streaming? At least this was not part of my plan in the beginning, but if that would interest, I can at least spend a lecture, if not like details, but at least give you the current state of art on what it is and what are the open problems there.
Second, but this comes with the cost of something, right? You have to sacrifice something else from your program to bring that.
But like if people would like to work on some problem, that is like, so it's like spending a lecture on bringing to people the new facets of streaming algorithm.
No, open problems would be very nice.
Yes. Okay. So the next lecture, I will finish this matching. Okay. And like an open problem, which is like, I don't know what level open problem is, these kind of things, open problem, but they're interesting open problem and it is worth to think about them. So for example, so if that would be interesting for people, then next lecture after my matching, I could fill that up with some interesting set of questions. Okay.